Welcome back, everybody. We are now moving on to section 6.5, periodic variations in element properties. So here we're going to describe and explain the observed trends in atomic size, ionization energy, and electron affinity of the elements. So this section name is really a fancy way of saying trends in the periodic table. So we're going to talk about these different periodic properties or these elemental properties and how we can use the periodic table to predict how they're going to change as we move from left to right, from top to bottom, etc. So there's a lot of different properties that each individual element has, and it varies as we change our electronic structure. So we start adding more protons and electrons. Now we have these different atoms, and that therefore makes new properties. And these are what govern our chemical behavior. So this all relates to those electrons in the outermost shell, our valence electrons. So these properties we're going to talk about include the size or the radius of our atoms and ions, their ionization energies, and their electron affinities. So we're going to talk about what these are and the trends in their properties, but just a little explanation before we get there. The radius of the atom is kind of self-explanatory. Ionization energy is the amount of energy it takes to remove an electron from an atom. And electron affinity is the atom's ability to take an electron. So keep those in mind, thinking about metals versus nonmetals and ionic charges that we've talked about earlier in the semester. So let's talk about a term called covalent radius. And this is 1/2 the distance between the nuclei of two identical atoms when they are joined by a covalent bond. So you have two atoms here, and they have nuclei. I hope this doesn't get flagged for being lewd. And we have this distance here. Half that distance is our covalent radius. All right, let's go ahead and erase that now. So going down a group. So if this crude drawing of the periodic table, going from top to bottom down a group, we're increasing our quantum number. So the period numbers are going 1, 2, 3, 4, 5, 6, 7. So we're increasing that n as we go down. And because of that, we're adding electrons to a bigger region of space. So now we're getting further and further from the nucleus. So because of this, the atom size and its covalent radius are going to increase going down a group. So if we have a nucleus, okay, there's our first shell, and then we add another n, another quantum number, and then another and another as we keep going down. So we're getting further and further from the center. Okay, so now we have this bigger distance and an overall bigger size of our atom. Related to that, we have this term called the effective nuclear charge, or Z effective, ZF. And what this is the pull exerted on an electron by the nucleus that takes into account repulsions by other electrons. So hydrogen only has one electron. So its nuclear charge, that one proton in the center, and its effective nuclear charge are the same because there's no other electrons getting in that single electron's way. But other atoms, every other atom, the electron that you're looking at is partially shielded from the pull of the nucleus by other electrons that are present. So core electrons are the ones that really do this shielding. Okay, they're in the core and they are shielding the outside electrons in the outermost shell so that they don't get as much of that attraction as the inner core electrons. So as we move from one element to the next across a period, we're increasing our nuclear charge. We're adding one proton, but the shielding's only slightly increasing because overall, electrons in the same valence shell don't really block the nuclear attraction experienced by each other very well. So they might shield each other a little bit, but not that much compared to how the core electrons shield. So we increase our protons as we move from left to right across the periodic table. And we're still in the same shell. We're in the different groups. So we're not really affecting that effective nuclear charge very much because we're staying in the same shell. So this means that our effective Z effective actually increases as we move from left to right. Since overall there's not very much extra shielding, adding more electrons to the same shell, then they're able to actually feel that pull more than as if going from top to bottom. Because going from top to bottom, we are really increasing the size. We're adding more orbitals to get in the way. So a way to kind of picture this, we've all been to little get-togethers, parties, kickbacks, whatever you want to call them, with friends. And there's the food. All right, let's see. What kind of food? We got some nachos. Okay, there's my plate of nachos and soda. Okay, it's soda. And I don't know. One time my family made a big old Thanksgiving turkey for my friends, so maybe some turkey. Beautiful drawings. So there's the food. And this was a pretty popular, there's a lot of people here. So they're kind of crowding around. And you and your buddies, maybe you're standing outside. There's like a little bonfire going or something. You guys are here chit-chatting around. And you're like, wait, I'm hungry. So you're feeling the pull from that delicious food. But there's all these people in the way. You and your buddies are all feeling this pull. And if you were to all kind of try to get to the food, you might bump into each other, but not too bad. You have some space. Whereas trying to get through all these people here, not so easy. Okay, so these people are like our core electrons. They're shielding us from the food. Okay, we can't feel or smell the food as well as we might want to, so it's harder to get to. You and your buddies are our valence electrons. And then, of course, the food is our nucleus with our delicious, delicious protons. So, but as we add more of our friends are joining us at the party. Okay, there's more of us, but we're still not really getting in the way of each other because we're still all around the bonfire. But now there's more of us, and maybe we can work together a little bit more so we can start smelling that food a little bit better. Because now actually we're adding more food too, because it's like, oh no, more people. Now we got some, I don't know, some burgers and more food, but this number of people inside the house that are surrounding the food, it hasn't changed. People are just coming outside to the bonfire. But we're getting more and more food. So now there's more food to go around too. So us and our friends, we can now go and eat and enjoy the fact that there's leftovers. Unless you're my friends who managed to eat a Thanksgiving meal that was probably meant for 20 people, and there were 5 of them, and they ate it all. And still didn't gain a pound. Meanwhile, I look at food and I gain like 10. Woohoo. All right. So again, as we go across a period, meaning from left to right, we have a higher effective nuclear charge. So the outermost electrons are feeling more pulled to the nucleus. So we can get closer to our food, so we can get closer and closer to it. So that means that the size of our atom and its covalent radius, therefore, decreases as we go across a period. So if we have our little periodic table here, effective nuclear charge gets bigger going from right to left and bottom to top. Okay, so, oh, I'm sorry. Increases going left to right and bottom to top. Okay. So the size of an atom, that's what I was looking at when I drew that arrow. The size of an atom gets bigger going from right to left, or gets smaller going left to right, and gets bigger going top to bottom. And here's a little table with an example. Our covalent radius, it shows our halogens. And as we're going from top to bottom of the periodic table, they're getting bigger and bigger. Okay, so they're a bigger covalent radius because we're adding more of those energy levels. So that's going to add more room. Here's a picture showing covalent radius for some diatomics, fluorine, chlorine, bromine, and iodine, are halogens, and how they measure them. Drawn a lot better than I did. And then you can also see in B, which is this periodic table here, covalent radii of the elements, and these are actually drawn to scale. And you can see that the radii increase going down a group and decrease across a period. So then, knowing that size increases going top to bottom and right to left, francium and cesium are our biggest elements. The reason I'm circling both is because francium is a little weird, so generally we kind of focus on cesium as being the largest. And then that means that fluorine, technically, is our smallest, or helium actually, sorry, is our smallest element. This is a chart showing the trend for atomic radii, and showing how it decreases as our atomic charge increases. So you can see at the top in purple, these are our group 1 elements, and at the bottom of each of these little peak areas, these are our noble gases. So you can see where the different groups start, or the different periods. And then as we start adding more protons, you can see the radii decreasing steadily. So as we increase the nuclear charge, we decrease our atomic radius. So related to that is the ionic radius, and we use this for measuring the size of an ion. So covalent radius is for the size of an atom, ionic radius is for that of an ion. Remember, a cation has less electrons, same number of protons as its parent atom. And what happens is as we remove electrons from the outer shell, now these remaining electrons experience a greater Z effective charge because now there's less negativity for them to experience. So your friends at that party, one of your buddies leaves, hey, more food for me because the amount of food in my food nucleus hasn't changed. So I can get closer to the food. A cation, therefore, is always smaller than the atom from which it's derived. Now, anions have more electrons than protons, and if we start adding electrons, we have greater repulsions and a decrease in our Z effective. So I've got more friends coming to the party, hanging out with me at the bonfire, but the amount of food hasn't changed. Okay, so now I've got someone else there to compete for the same amount of food. So because of this now, I can't feel that food as much. I've got more room. So the valence electrons are further from the nucleus as we add electrons to make anions. So anions are always larger than the atom from which they are derived. Here's an example, figure 6.32, showing you aluminum versus the aluminum 3+ ion. Okay, we take away those 3 electrons from aluminum, and look how much smaller it gets. And then sulfur, we add 2 electrons, and it gets a lot bigger. Now, if you have an atom and ion that has the same electron configuration, we call this isoelectronic. So that means you write down the electron configuration and it's the same. For example, nitrogen 3-, O2-, F-, neon, sodium, and magnesium 2+, and aluminum 3+, all have this electron configuration because they have a total of 10 electrons. So this also shows you nitrogen, oxygen, fluorine, the sodium, magnesium, and aluminum ions, what they have to do to have a noble gas configuration. All of these have the same configuration of a neon atom, neon being a noble gas. So nitrogen, oxygen, and fluorine gained electrons, which means they got bigger, whereas sodium, magnesium, and aluminum lost electrons to have the same electron configuration, meaning they got smaller. Another example, phosphorus, phosphide, sulfide, chloride, argon, potassium ion, calcium ion, and scandium ion, again, are isoelectronic. So these guys are isoelectronic to argon. And then again, you can see what they had to do to have that noble gas configuration to be the same as argon here. So what really is going to determine the size of the overall atom or ion when they're isoelectronic is the number of protons. So what this all comes down to is the higher the nuclear charge, the smaller the radius for a series of isoelectronic ions and atoms. So this brings us to our next property, ionization energy. So what this is it's the amount of energy required to remove the most loosely bound electron from an atom in its gaseous state in the ground state. And this is called its first ionization energy, or IE sub 1. So you've got whatever your atom is in the gaseous state, and it becomes positively charged, gives off an electron. And then you can put in more energy to take a second electron out for the second ionization energy. So now you have this X+ atom becoming a 2+ plus another electron. And then there's the third ionization energy, and so on and so forth. You always have to put in energy to remove electrons from atoms or ions. So that means since we're putting in energy, this is an endothermic process. And the energy values are always, always positive. So as we increase in size, though, our ionization energy is going to decrease because it's bigger. Okay, so you have less pull on the electron, so it can give it off easier. It's not holding on to it as much. So I have this picture here, a book that almost all of us read as little kids, The Rainbow Fish. It's got the fish with the pretty scales, and after an epiphany realizes that he wants to share his beauty with the world, kind of like a nice big atom wants to share their electrons, especially a metal or something with a low ionization energy. It's like, here's an electron for you. Oh, I can still give away another electron. I still have a lower energy. Okay, so the rainbow fish, think of it as our nice big atom with some electrons to go around. So, our first ionization energy, think of this with size. Since our size gets bigger as we're going down the periodic table, okay, size is increasing, that means our ionization energy decreases. So the higher up on the table, the higher the ionization energy, because these are smaller atoms. Going from right to left, okay, is the other way our size increases. So it's biggest on the left side, left bottommost of the periodic table. So our ionization energy thus is going to increase going left to right, because now we're getting smaller going left to right, which means we have a higher effective nuclear charge, which means it's going to take more energy to pull those electrons off. And yes, of course, there's some deviations. But this also tells us that our ionization energy is going to be highest for nonmetals and lowest for metals. And this makes sense, right? Because this is about taking electrons off. Metals are the ones that give away electrons, whereas nonmetals don't want to give them away, they want to take electrons. So it makes sense that they should have a higher ionization energy because they don't want to give them away. So here is a graph showing you the first ionization energy of the elements, plotted against their atomic number. And you can see our noble gases up top with the highest. Makes sense, right? Because not only are they our smaller elements, they also have a nice full valence. They're nice and stable. They don't want to give away their electrons. Okay, and then you see our hydrogen also, and then our group 1 alkali metals on the bottom. Of course, there are some exceptions to the rule, but this is a generalization. And so here's the periodic table giving you some first ionization elements or energies of some of the elements. You can see that trend. You can see it getting bigger as we go from left to right. For instance, in period 2, you can really see it. And you can see it also going down, looking at group 1, going from top to bottom. Hydrogen is kind of our exception. It kind of, for this trend, belongs more over here above the halogens. So let's talk about some deviations. Beryllium has a higher first ionization energy than boron. And this is because the electron removed to ionize beryllium is an s electron. So it's got this 2s2, this nice filled s orbital. Whereas boron goes 2s2, 2p1. And it's got this single electron in the p orbital. The energy of the subshell is going to increase as we increase our L. So an s electron is harder to remove than a p electron in the same shell. So it's a lot easier to lose the single p electron than it is to lose one of these electrons in the s orbital, because the p is higher in energy. Another example, oxygen has a lower ionization energy than nitrogen. So this is because nitrogen, okay, it's 1 less than oxygen. Just kind of draw it here. Nitrogen has these 3 unpaired electrons in the p orbital. So it's 1s2, 2s2, 2p3. And in oxygen, we have in the 1 pair of electrons, and it's actually a lot easier to get rid of 1 electron that's paired from that p orbital to have 3 unpaired electrons. It's a lot more stable that way. And that gets rid of the electron-electron repulsion in that degeneracy. So it's more energetically favorable to remove that 1 electron from oxygen than removing 1 from nitrogen. So removing an electron from a cation is a lot harder than removing it from a neutral atom, because now you have more electrostatic attraction to the nucleus from the electron, because now we have that positive overall charge, so the electrons are much more attracted. They have that stronger Z effective. Same thing with removing an electron from a cation with a higher charge is more difficult than removing an electron from an ion with a lower charge. So ionization energies for an element always increase as we go from the first to the second to the third and so on. And here's a chart showing you some elements, and you can see like for potassium, our first ionization energy, 418.8 kilojoules per mole. Trying to go up to the second one, though, that's a huge jump. Okay, up to 3,000, so almost 2,500 kilojoules per mole needed to do that next jump. Calcium, we go from 589.8 to 1145.4. Not too bad, but trying to go up to the third ionization, boom, we've gone up over 3,000 kilojoules. And this makes sense, right? Potassium's in group 1. It's a K+. Calcium is a 2+. So you can see like scandium, we go 1 to 2 to 3, not so bad. But then to 4, huge leap. So you can see this trend happening. So there's always some really large increase in the successive ionization energies for an element. And this is where you hit your core electrons, which are way harder to remove than the valence electrons because they're nice and stable. That's that noble gas configuration. They don't want to be taken off, so you got to put a ton of energy in to really be able to pull them out. So for instance, scandium and gallium have 3 valence electrons each. And you can see that after the third ionization, there's a large increase. So I showed that for scandium, and then for gallium, same thing. 1, 2, 3, huge increase to the 4th. So that corresponds with those 3 valence electrons. Our next property is electron affinity. And this is the energy change for adding an electron to a gaseous ion, or atom, to form an ion. And an anion at that. So we take our gaseous element and we give it an electron to give it a negative charge. Depending on the element, this can be endothermic or exothermic. Some elements release energy when the atom takes an electron, so you would have a negative energy. Other elements, you have to put in energy, so it's positive energy and positive electron affinity. So negative electron affinity is when you have energy being released when the atom takes an electron. A positive electron affinity is when you have to put in energy for the atom to accept the electron. As our effective nuclear charge, or Z effective, increases, it's easier to add an electron because we have this higher affinity for the electrons. We have a higher effective positive charge, so then that negative charge is going to be more attracted to it. So electron affinities become more negative across a period, meaning they're higher. They want those electron affinity. They want those electrons. Which makes sense. Those are our nonmetals. Now, of course, there's some deviations. There's always deviations. Noble gases, for instance, group 18. They are completely filled. They're nice and stable. So if they want to take an electron, it has to go to a higher energy level, a higher N. They really don't want that. Group 2, okay, our alkaline earth metals, have a filled S subshell. Okay, it's NS2. So if you want to add an electron to them, then you again have to go up to a higher subshell. Group 15. Okay, so this is like nitrogen, phosphorus, arsenic, antimony, and bismuth. These guys have a half-filled p subshell, NP subshell. So the next electron would have to be paired with an electron in that NP subshell. So that takes more energy because you have to, again, pair it with something. So because of that, the electron configuration kind of messes up the stability. The stability is messed up, and then that is what disrupts the electron affinity trend. So here's some examples here. For instance, you can see our electron affinity, how it changes going from left to right. Remember, our alkaline earth metals are a little weird since they have that filled S subshell. You have to put in energy to get them to take it. Nitrogen has a relative 0. Okay, and then you can see these lower electron affinities for group 15. But overall, you see that the nonmetals have a more negative electron affinity. Okay, meaning they release energy when the electron is put in, and they get more stable. So that concludes chapter 6. I hope it made sense for you guys, and you're now able to do the homework and the quizzes. As usual, I will be doing a homework video, so make sure you send me in any questions. And I hope you're all doing well, and I will see you all soon.